All right, so let's go ahead and get started. So uh, thanks everyone for being here for our colloquium talk this week. And we're sort of nearing the probably towards the end of the semester, and we've still got a few more talks left though. So be on the lookout for those in the coming weeks. And today we have um, Dr. Kazuki Nakano. Is that how I say your?
Yes,
Yeah.
Keisuke Nakano, yes.
Yeah, thank you. And they're from the, I think it's research in electrical and communication, or let me see. I like to say where you're from, and I closed the thing on accident. Yeah, so they're the Research Institutes of Electrical Communication. And today they're going to be telling us about Turing machines with syntactic restrictions. And I'm pretty excited about this presentation. I also invited some students from our Theory of Computation course who are learning about these things right now. So it's nice and relevant to some of our students. And so thank you, and I'll let you take it away. And again, thanks a lot for giving this presentation. I know it's late for you and early for us, so.
Yeah, very. It's 10 p.m. So okay, can I start?
Yeah, go ahead.
Okay, so thank you so much for the invitation. I'm Keisuke Nakano from Tohoku University. I feel really honored to speak in this series. I would be happy to, if you get interested in this work, and collaborate with you if possible. So today I will give a talk about Turing machine with syntactic restrictions. Since this research may sound just theoretical, so I will start with some programming language as an introduction. So first I'd like to ask a question. So what is your favorite programming languages? So C, C++, Java, Python, Ruby, Haskell, OCaml, etc. So there are plenty of programming languages in the world. So if you have the best programming language, then you may have some reason why you think so. So what are the differences among them? So some programming languages are easy to write, but some of programming languages are good performance. So you may select the programming language depends on the objective and the situation you face. So how about the fundamental difference? So even though the programming languages are different each other, you might use the other programming language instead of your favorite one. So in that sense, we might say that that difference is not fundamental. So indeed, most of programming languages have the same expressive power, as you may know. So all programming language can express any computable functions. So what is a computable function? If we consider the function over integer, a computable function is formally defined like this. A partial function f over integers is said to be computable if and only if, for any integer x, the value of f of x can be computed in finite time whenever f of x exists. So you may have had the most general purpose programming language like C, Java, Python can implement only but all computable functions. So this, in other words, most programming languages are Turing complete. So if we have the set of the functions which can be implemented in some programming language, then and we have the set of the all computable function, then they are exactly equal. The notion of Turing completeness was named after Alan Turing. Of course, all of you know that, but who introduced the most typical computational model called Turing machine. So Turing machine is a computational model that can describe only but all computable functions. So it works on the tape and stores some symbols. This is tape, this is the head, and this is state. So next configuration of the tape is determined by the previous configuration of tapes. So that so that depends on the current state and what symbol is pointed by the head. So for example, it may relate in symbols at the head like this, 1, 2, 0, and it may move the head to the right like this. So a Turing machine performs as a computable function, and the output, the input of the function correspond to the initial configuration, and the output corresponds to the final configuration. And so in this talk, we consider syntactically restricted programming languages. So occasionally, we may only need some restrictive type of function instead of the all computable functions. So in this case, it would be better to have the restricted programming language in which the only such restricted function can be defined. For example, when we only need a total function, which terminates for any input, we may design the programming language by forbidding the loop constructor and recursion. Then all function always terminates, so we can define always total functions. For another examples, when we only need injective functions, which are reversible function, we may design a programming language by allowing to use only reversible operations like this incrementalization by constant. Then this is reversible, so it is always defined injective functions. However, it is not trivial that these kind of the restriction are not appropriate or not. So they might unnecessarily restricted too much. So it is non-trivial to show the expressive power of this kind of the restriction. But we could use the Turing machine as a computation model if we have no restriction. How should we do for restrictive functions? So we need the exact computational model that covers only but all computable functions satisfy the properties. So in this context, there is a success story of one of the computational models, that is reversible Turing machines. So reversible Turing machine is a Turing machine whose transition rules is locally forward deterministic and backward deterministic. Forward deterministic means that the next configuration is uniquely determined by the previous one. The backward transformation, backwards deterministic means that the previous configuration is uniquely determined by the next configurations. Under this restriction, consider a computation from the input to the output, where the initial configuration corresponds to the input and final configuration corresponds to the output. Because of the backward determinism, there is no other backward step for each configuration during the computation. So it means that there are no other input that generate the same output. So therefore, it is easy to see that a reversible Turing machine always computes an injective function. But what is surprising is that the opposite does also hold. So any computable injective function can be defined by an reversible Turing machine. And this fact can be stated as these theorems. any computable injective function can be computed by reversible Turing machine. It means that a reversible Turing machine is expressive enough as a computation model for injective functions. This computation model exactly covers the set of all computable reversible Turing machine, reversible injective function. So actually, the sum of reversible programming language are shown have sufficient expressive power by simulating any reversible Turing machines. For example, in this way, the reversible programming language Janus and R-while are shown to be R-Turing complete. That is, the programming language is expressive enough for injective functions. So what is interesting is that since the restriction for reversible Turing machine is just syntactic, so it is decidable whether a given Turing machine is reversible Turing machine or not. Also, it is undecidable whether a given function is injective or not. So how about the other properties other than the injectivity? So we will consider the involutariness and idempotence as such properties, as I will introduce later. So my today's talk about restrictive Turing machine can be summarized by these tables. At first, mathematically, a function f should satisfy this semantic property. So x equal y implies f of x equal f of y. So if we consider the deterministic Turing machine, then it is easy to see that they always compute a function because of their forward determinism. It is known that as the Church-Turing thesis that this computation model can define any computable function. And for injective function, which satisfy the semantic property like this, f of x equal f of y, then x equal y. We can consider the reversible Turing machine that is locally forward and backward deterministic. And we have seen before, a reversible Turing machine always computes an injective function, and this computation model exactly covers all the computable injective functions. In this talk, we focus on the other two properties of functions. One is involutariness, and another is idempotence. Now I just skip the detail. I will explain this later. So in this talk, first I will give a brief introduction of Turing machine with their formal definition and semantics. And also I will review some results on reversible Turing machines. Then I will introduce the two kinds of restrictive Turing machine called involuntary Turing machine and idempotent Turing machines. Because of the time limit, I will just briefly mention about the robustness of universality of these Turing machines before I conclude this talk with summary and future work. So let's start with the formal definition of ordinary Turing machines. So there are many variants of the Turing machine in the literature, even though their expressiveness are equal. Our Turing machine is specified by 5 tuples, set of state and set of tape symbol, except for the blank symbols that is denoted by the square in this presentation, and initial state and final state, and a set of transition rules. Our Turing machine works on the final multiple doubly infinite tapes, which have neither left nor right ends. So each tape has a head, and configuration is represented by the pair of the state and the condition of the tape. So when we only consider a valid run in which the initial configuration and final configuration have this form. That is, all left cells of the head must be blank. All the left cells of the head are blank. And the right of the head must be a sequence of the symbols following the blanks, like this. So this restriction is required to define as function semantics we will see later. So let's see the form of transition rules. Each transition rules of Turing machine is given as a triple, like this. The first and third are the source state and the target state, respectively. So, and the second indicates the action of each tapes. So this is a K-tape Turing machine, so we have the K actions. So there are two kinds of the actions called the symbol action and move action. So symbol action have this form. So which means that if the tape symbol at the head is a SI, then replace it into SI prime. So for example, when running the 4-tape Turing machine, and this configuration is updated into this one through this transition rule with symbol actions. So A, F, O, C, A, F, O, C must be rewritten into the O, B, A, K. So for the head, A, F, O, C must be rewritten into the O, B, A, K. So without moving the head. Another action is a move action. Move action has 3 types of actions: the left, stay, and right. So dot means the stay of the moves. So without just means without moving. So for example, this configuration is updated into this one through this transition rules. The right, stay, left, and right. So this head must be moved to the right. This head doesn't move because of the stay moves, and this move to the right, left, and this move to the right. So this is a definition of transition rules of our Turing machine. Now we are ready to define the determinism of the Turing machines. So deterministic Turing machine and reversible Turing machines. So now let me introduce a notion of determinism. So deterministic Turing machine is defined as a forward deterministic Turing machine. The forward deterministic means that if there are 2 distinct transition rules that share the source state, Q, then their action must be symbol action, not move action. And also that symbol action with different input. From now on, we simply call the Turing machine instead of the deterministic Turing machine. So reversible Turing machine is both forward, backward deterministic, so that the previous configuration is uniquely determined. The backward deterministic means that the similarly defined like forward determinism. Just if there are 2 distinct transitions sharing the target state, then their action must be symbol action with different output, so that the previous configuration is uniquely determined. So the semantics of Turing machine is defined in this way. So following the Axelsen and Gluck's work, we take the function semantics for Turing machines. Recall that the invalid run, the initial and final configuration has these forms. So the left of the head are all blank, and here is the sequence of symbols and blank. The semantics of the Turing machine is defined as a function whose input and output correspond to the initial and final configurations. So the semantics of the K-tape Turing machine is a function that takes a K-tuple of words and returns the K-tuple of words. But sometimes, we like to represent a function whose input and output has a different number of tuples. So we adopt some convention taken by the Axelsen and Gluck's. This is the convention. So if we have some tapes must be empty at the initial and the final configuration to be a valid run, then the semantic function can ignore such tapes. For example, the semantic function for the 3-tape Turing machine, if this equation holds, so only where the x1 and x3 and y2 are empty, then we can identify this function with this function. So it takes just the x2 and return y1 and y3. So x1 and x3 as the first and third input, and the second output is ignores, because the initial and the final they are always empty at the initial and the final configuration. So this is a convention on the function semantics. So, and now we like to see the characteristic property of the reversible Turing machine. So let us introduce the syntactic inverse of the Turing machine for that. The syntactic inverse can be defined by the swapping the initial and the final state, like this, and inverting all transition rules. The inverse of transition rules is defined like this. So swapping the source and target and inverting the actions. The inverse of action is the naturally defined like this. X1, this is a symbol action. S1 to S2 is its inverse is S2, S1. And left move, the inverse of left move is a right move, and so on. Then we naturally have the proposition for the reversible Turing machines. Inverse of the reversible Turing machine is also the reversible Turing machine, and its semantics is inverse. So this is easy to prove that. So now let us review again an important result for reversible Turing machine. This proposition states that as long as the semantics of given Turing machine is injective, then there exists reversible Turing machine, the equivalent Turing machine, T prime. So some of the Turing machine, there exists the non-reversible Turing machine whose semantics is injective. So even if the transition rule says backward non-determinism here, but this path always holds invalid position of as the input. Then we may say that this is injective. This output always generated by this input. But so in this case, this is non-reversible Turing machine. But this proposition says that an equivalent reversible Turing machine always exists, even for this kind of the non-reversible non-reversible Turing machine. So as a corollary, any computable injective function can be defined by an reversible Turing machine. This is the main statement, the expressiveness of the reversible Turing machine. So let's start, move to the other two syntactically restricted Turing machines. So first, introduce involuntary Turing machines. And that is a computation model for involution. So what is an involution? First, as an involution, also called involuntary function, is a function that is own inverse. So an involution is a function f satisfies this formula. If you apply that twice, then return the input itself. So in other words, so f of x equal to y, if and only if y, f of y equals to x. This is called involution. So this is a function that is its own inverse. F equals f inverse. So this is a particularly kind of the reversible that is injective function. So there are many applications of the involutions in the everywhere. So for example, in mathematics, it is well known that Donzagiers have given a one sentence proof to the Fermat's theorems on the sum of the two squares. And in computer science, there are cryptographic systems based on the involuntary function, like a one-time pad or the RC4 and so on. So in addition, the involution occurs in the context of bidirectional transformation, which is actually the motivation for this work. Anyways, I'd like to introduce the involuntary Turing machine. So Turing machine is said to be involuntary if there exists a function psi over the states that satisfy the following two conditions. The first condition is that that psi maps the fy, the initial state to the final state, and like this, and also it's this condition. This psi is involution. This is also involution. So it takes a state P, return the Q, then this psi maps Q to P. So they must be so if, so because of this condition, psi of the final state must be the initial state. So we have this relationship through the psi. And also for some state, we have some correspondence, and also the sum of the state just self-correspondence through the psi. So this is the first condition of the involuntary Turing machine. Another condition is that if we have some transition rule Q1 to Q2 through action A, then there must be so now we have the correspondence because of this restriction. We have some state through the psi, like this. And then we have the other transition rules, P2 to P1, with the inverse action of this action. So this is the second condition of the involuntary Turing machine. If we have these conditions, then this Turing machine always computes the involution. Let's see how we can say so. So for example, we have some run of this Turing machine. So this is the initial configuration. This is the final configuration. Then now we have the first, the second condition. We can recover this previous configuration from this state to this state. So similarly, so we can have this backward run because of this rules. And also we have this condition, C of the initial state is a final state, and C of the final state is the initial state. Then we can say that this is also the valid run for this Turing machine. It means that if it has takes this input, return this output. But also this if this Turing machine takes this as the input, then it returns this output. So this is an involution. So this is why if we have these two conditions, then we can always compute the involution by this Turing machine. So we can say that T is an involutory Turing machine, then this must be the involution. The semantics must be involution. So this is the example of the involutory Turing machine. It will play the important role to prove the expressiveness of the involutory Turing machine. So this is a neg1. T neg1 is the full semantics is like this. It takes bx. B is the first. This is a two-tape Turing machine. This takes a pair and return the pair. And the first component of the pair, input pair, then it starts with the 0, 1, 2, or 2, and return the bar, B bar, that is, if the B is 0, it returns 2. If B is 1, then B bar is 1. So, and this is if input is 2 and the output is 0. So this is meaning of the B bar, and the other words doesn't change anything. So if you take the 2021 and 22 OCD, then the first of the first symbol of the first component just change it to the 0. So we can define this kind of the function by this Turing machine, involutory Turing machine. I do not go further details, the definition of this Turing machine, but you can find the correspondence between the transition rules, which requires involutory Turing machines. So we have the C map for these two states. Then we can find this transition rule correspond this one. So Q0 to Q1 is P1 to P0, and this right move is a left move, and so on. So here is also another relationship over transition rules. Then we have this one can be reversible. This is the inverse run is also the valid run. This is because of the involutory Turing machine. So this is the example of the involutory Turing machine. So please remember that T-neg1 computes this function. The first symbol, just first symbol of the first component will be changed like this: 0 to 2 and 1 to 1 and 2 to 0. And sorry, so it's strange. So, but how about the T-swap that computes this function. It takes a pair x and y and return the pair y and x. This obviously this is involuntary, but it is actually it is difficult to define this kind of function as an involuntary Turing machine, because naive implementation breaks the restriction of the involuntary Turing machine. For example, we write in this way. First, this is the input. First, find the right end moved by moving the heads simultaneously, and then get the right end. Then goes back the head, swapping the symbols T blank, so blank and T, so it must be a T and black, and swap all of the symbol to get the swapped result. But obviously, this is asymmetric. This run is asymmetric because the first move just without changing the symbols and changing the symbol for swapping later. So the inverse run cannot be the valid run. Because this inverse run must be first the changing the symbol, and then without changing the symbol to back to the head position. So that is not symmetric, so it cannot be involuntary Turing machine. So how can we define this kind of swap function as an involuntary Turing machine? So to solve the problems, we observe the other property of the involuntary Turing machine. One of the interesting and important property is involuntary Turing machine is that involuntary Turing machine is closed under conjugation with reversible Turing machines. To understand this property, let me start with the case of the ordinary involution, that is all involution is closed under conjugation with injective function. So let's F the involuntary involution and G is the injective function. Then we can say that this is a conjugation. G inverse compose F compose G. This is also involution. So it is easy to prove that by simple calculation. So if F is involution and G is injective, then we can construct other involuntary involution. So involuntary Turing machine also have the similar property as stated in this proposition. If we have the involuntary Turing machine Ti and reversible Turing machine Tr, then the syntactic concatenation Tr inverse compose Ti compose Tr is also involuntary Turing machine. So this is the involuntary Turing machine. Then this can be the involuntary Turing machine. So it is easy to prove this proposition by extending the Psi to map the state between these states of Tr inverse and Tr. So this we just make the correspondence between the states through the Psi. Then we are ready to define the T-swap. So we can construct the involuntary Turing machine T-swap, which semantics as a swap function. First, we consider the function f. It takes a pair x and y and return 0x and y if f less than y, x less than y in lexicographic orders. In other case, it returns 2yx. If x equal y, then it just returns 1 and x, the pair of 1 and x. Actually, it is easy to see that this is an injective function, so we can construct a reversible Turing machine for this function f. Then, now we can construct a T-swap by composing the STF inverse and T neg 1 and TF, because if x less than y, then this function, this Turing machine computes in this way. Xy will be 0xy because of the definition of the TF. And T neg 1, this first symbol will be replaced with 2, so 2x and y. And now we apply the inverse function of this function, then we will get yx, the pair of yx. So this is a swapped one from the input. The other cases also have we found the always swapped result. So we can say that this function, this Turing machine, always compute the swap function. So this is the T-swap, definition T-swap. So we can use this function to show the expressiveness of the involuntary Turing machine later. So expressiveness of the involuntary Turing machine is stated in this way. If the semantics of Turing machine is T is involuntary, then there exists equivalent involuntary Turing machine. So this is proved in the next slide. So actually, you may know that as you have seen that the semantics of the involuntary Turing machine can be involuntary. That is examples of naive swapping Turing machine. So this is asymmetric. So it is, even if it is an involution, but it cannot be the involuntary Turing machine as a direct implementation. But this statement says that there exists an equivalent involuntary Turing machine. So as a corollary, we can say that any computable involution can be computed by an involuntary Turing machine. So proof is in this way. So first, we have the Turing machine, but whose semantics is involuntary. So it cannot be, it may not be the involuntary Turing machine, just a Turing machine. So now we consider a function R like this. It accepts the word and empty word and returns the T of D and D like this. So actually it is injective because of the output just copy from the input. So it must be the injective. So this, because of the injectivity, we can construct a reversible Turing machine TR like this. So it can be reversed. It is reversible, so we can define the TR inverse. So it takes this one, T of D and D, then it returns a D and empty words. Then we can construct a involuntary Turing machine, an equivalent involuntary Turing machine, by concatenating TR and T swap and TR inverse, as shown below. So if we have the input X and empty words, because the restriction of T of R, it must accept just word and empty words. And we have this pair, T of X and X, and T swap computes the X and T of Y, because this is a swap function. Then, and note that this X is equal to T of X, because of the T is the involuntary, so we can replace it X into this one. It is they are equal. Then now we can run inverse of TR. So we have the T of X. So now Z is T of X. Then we have the T of X. So we can see that this is the input X, and the output is a T of X. So this computes the same function of the T. So this is a proof of the expressiveness of the involuntary Turing machine. So I have not so time to explain the idempotent Turing machine. So, but okay, I hurry to explain. So, what is an idempotent function? Idempotent function is the twice application is the same as the single application. So, equivalently, the f of x equal y implies f of y equal y. So just twice, the second application is always generate the same output. So there are many applications of the idempotent function, for example, the string sanitizer preventing the double encoding attack. So, okay, I will skip the application now. So let's see the definition of idempotent Turing machine. A Turing machine is idempotent if the set of state can be split into the Q1 and Q2, split into the two groups, and then we have some map C Q2 to Q1, the total function, which satisfies the following four conditions. The first, it's split into the set in the for all of the states, and the final state and initial state must be in Q1, and final state must be Q2, and the C of the Q F must be the C just QI. So this is the first condition. The second condition is if we have there are no rule from the Q2 to Q1. This is the second condition. The third condition is that if we have the transition rule in Q2, then there exists the counterpart in the Q1, pussy Q2 to pussy P2. This is the correspondence, and also must be the inverse of this action. And the fourth condition is that if we have the Q1 to Q2 transition rule, then there exists other state in Q1 can be computed by the psi from this state with null action. A null action means that if A is a move action, then a null must be the stay move or stay. And if A is a symbol rule, then a null must be the all symbol and not change it. So this is a null action. Okay, so this if we satisfy the four conditions for the idempotent, four conditions for the Turing machine, then it could be the idempotent. So let's see how this condition forced to compute the idempotent function. So let's consider this some valid run. Q0 is this is the initial state and this is the final state. So if we have the input x, then return the y. So it means that t of x equal ty. This is the computation of this one. But because of the first condition, this in the Q1 and the final state in Q2. And because of this condition, no transition rule, the Q2 to Q1. So there exists some border bridge to Q1 to Q2 world. So there are a single rule here. And because of the third condition, if there exists the so it must be, if we have the Q2 transition, then there exists a counterpart of this rules because of the third condition. Sorry, it must be remained. And finally, if we have the transition from the Q1 to Q2 here, then there exists a null action here. So this configuration must be the same. Then now we have, this is a QF, QN is a QF. So and QF is a Q1 initial state. Then so this is also the valid run. So it means that this is the same as this one. So this is a Y. So we can say that T of Y is equal Y. So it means that T computes the idempotence. So we can say that if T is the idempotent Turing machine, then T computes the idempotent functions. And so I have no time to explain this example, but T copy, this takes X and Y and return the pair of the Y of Y. This is idempotent function, and it's actually defined by this idempotent Turing machine. So it satisfies all 4 conditions. So just I explained this function. And also the idempotent Turing machine also satisfy the closed under conjugation, closure property of the under conjugation. So okay, I skipped this property, but the proof of the idempotent Turing machine also satisfied such expressiveness. If the semantics of Turing machine is idempotent, then there exists the equivalent idempotent Turing machine. So it is easy to define the non-idempotent Turing machine that is whose semantics is idempotent. But actually, there exists an equivalent idempotent Turing machine, as we have seen for the involuntary Turing machine. So we can say that any computable idempotent function can be computed by idempotent Turing machine. So I have no time to explain the proof, but I can construct idempotent Turing machine equivalent to the original one, like this. So it computes X to the T of X because of the idempotence of the Turing machine. But I have no time to explain this proof details. Sorry. And also the other property of the Turing machine also holds for any restrictive Turing machines. First one is robustness, that is tape reduction theorems. So first, robustness means that you may know that an ordinary K-tape Turing machine can be simulated by a single tape Turing machine. This property also holds a reversible Turing machine and involuntary Turing machine and idempotent Turing machine. If you have the K-tape, some such Turing machine, then it can be simulated by a single tape one by appropriating and tuple encoding. Other property is universality. Universality means that if we, okay, I haven't also time to explain. But universality means that any other reversible Turing machine can be simulated by, there exists a reversible Turing machine that simulates arbitrary reversible Turing machine. So that is similar to the definition of universality of the Turing machine. And also that holds for also for the involuntary Turing machine and the idempotent Turing machine. So let me conclude with my talk with summary of further work. So I have introduced the 3 types of restricted Turing machine: reversible Turing machine, and idempotent Turing, involuntary Turing machine, and idempotent Turing machine. So let me explain the 2 directions of future research, further research. The first, I'm interested in how about the other property of the function, other than injectivity, involuntariness, and idempotence. And also that I have interested in how can we design restrictive programming language. so because of the success of the reversible Turing machine, I like to design the other, for example, involuntary programming language or some idempotent programming language, which covers all of the computable involution or the idempotent functions. This is the end of my talk. Thank you for your attention.
Thank you very much. Yeah, this is very interesting stuff. Does anyone have any questions?
I have one. Can you hear me? I have a question, but I think you cannot hear me.
Sorry, I cannot hear you. Can you?
Can you hear me?
Yes, I can hear you, but
okay, great. Yeah. So does anybody have any questions? Here we go. Okay, so looks like Clement has a question. So go ahead. If you need to type it in the chat, that's okay. Or... Okay, yeah, Clement has a question. He said it's a bit of a long one. He's gonna type it in the chat because his computer his mic isn't working correctly right now. So one thing I think I missed, and you might have said it, because I was kind of fielding. I have to go through many screens, but I was wondering, when you add these restrictions, are they still equivalent to full Turing machines, or they become less, I guess, expressive?
What it means full Turing machine?
Yes, so I guess just the ordinary definition of a Turing machine, as opposed to having these additional constraints.
You mean the other types of the full
Yeah,
Turing machine? Yeah. For example, the one maybe. So our Turing machine is a bit special because of this separation of the actions.
Yeah.
So if you consider maybe the standard Turing machine in the textbook,
yeah,
always these mixtures. So it's check the symbol and it change the symbol and move to the left.
Right. Yeah.
In that case, it's difficult to define the inversion because of it's just see the symbol and replace and move. So that the inverse of that action must be the move first and to see the next one and move and change the symbol. So that is
right.
the good.
That makes sense.
Inversion. So this is why I use this kind of the convention definition for the.
Yeah, that's cool. Yeah. Thank you. Yeah, I think so. Can you see the chat? I think Clement has posted 2 questions.
Sorry, I cannot see the.
Okay, chat. That's okay. I can read it. So he says he has 2 questions. So one is, it is generally preferable.
I can see that. I could see.
Oh, okay, yeah, great.
So I have 2 questions actually. So basically, it's generally preferable to use constructive reasoning when you have the chance. But is there any strong reason to prefer reversible computation if given the choice?
So can you hear me?
Yes.
Yeah, we can hear you.
Okay, so sorry.
I have too many mics. So thank you so much. My first question is, so like you can have constructive and non-constructive proof, and if you have the choice, it's generally better to take constructive proofs.
Yeah.
Like imagine I have an algorithm and I have a reversible way of writing it and a non-reversible way.
Yeah.
What would be a good argument to say, oh, you definitely need to write it the reversible way and to execute it on a reversible machine instead of writing it on an irreversible way? Like, what would be the compelling argument? Because for constructive math, it's easy. You say, well, here's the witness. Like, you can have the actual witness, and it's better not to use excluded middle, that sort of thing. Is there a very strong argument, similarly, for reversible computation?
Yeah, that is a good question, because actually it is it's difficult to get the this is one of the research topics to compute to obtain such a good reversible Turing machine from the usual.
Okay.
Because actually I didn't show that about the proof of the expressiveness of the reversible Turing machine, that is any injective function can be computed by the reversible Turing machine. This the proof is actually very tricky, so and actually requires inefficient computation there. So maybe it is not practical so far. So maybe actually it's my proof for the involuntary Turing machine, idempotent Turing machine also depends on that proof. So
okay,
it must be improved for.
Okay.
I think.
Okay, so thank you. And my second question, which is a bit related, is that from my limited experience, it is very difficult to design algorithm for reversible computation. Like just adding two numbers is tricky, actually. If somebody had to show me, or you can add two numbers in a reversible way, like I couldn't think of it myself.
Yeah.
By working with those restricted Turing machine models, do you feel you're getting better insight on how to write reversible algorithms? And do you think you could find any algorithm that are reversible and that are more elegant or more efficient or something? You seem to say no. You seem to say that's more difficult and more
difficult. I think that currently my results just are theoretical, so I do not consider some practical one.
Okay.
But,
okay.
But we can design some programming language with some such restriction, which is some kind of powerful to sufficient expressive enough for such function with property.
Okay.
Great. Anybody else have any questions before we adjourn? All right. Well, thank you very much again for presenting today. And I know I enjoyed it. And yeah, have a great rest of your, I guess it's nighttime now, right? Yeah. So I guess you can just go to sleep.
Thank you.
Yeah, thank you very much. And thanks, everybody.